Thank you all for joining for our October meeting. We have a few things to get started here, a few matters of member business before we move forward with our presentation. Just really quickly to let everybody know, we are having a chapter relaunch, and Chuck, our chapter president, will go into that a little bit more in detail here in just a few minutes. But just so you're aware, we do have a new membership drive that's associated with that. You've probably gotten a few emails from me asking you to re-sign up on the website. If you go to the ISC Squared Huntsville chapter website and sign up for membership on the site there, you'll be re-added to our notification list, but I'm going to try not to make use of the old notification list moving forward. We are shooting for having a regular member meeting starting here either on the third or fourth Thursday of each month moving forward. And those may take various forms, but we're trying to get back into a regular rhythm moving forward.
Okay, the camera's on again. Yeah, hi, good evening. And some of you I know, some of you I don't know, but hopefully we're going to meet sometime soon. As Noel was mentioning, the whole thing with complete stoppage during COVID, that's really what led us to where we are today and why we're doing what ISC Squared calls a chapter relaunch. And it's basically, they've had this experience with other chapters along the way. And it's their way of helping us out in getting back up to speed. Okay. And getting back up to speed, getting participation from membership, growing the membership, doing those kind of things, and actually expanding out the leadership in some cases. And the most important part of that is that in so doing, will remain in an active standing with ISC Squared, which is most important to us because we are affiliated directly with them. So go ahead, Noel, next one. Okay, who is relaunching? Okay, like I said, there's other chapters that have done this. There's other chapters doing it now. Most recently or currently, it's Huntsville, us, Northeast Florida, and the New York Metro chapter who are going through these relaunches. So it's going to be interesting. We'll be reaching out to them to talk to them about how it's going with them and the things they're doing as well. Hopefully learn a little bit, share a little bit in what's going on. But it's not a new thing. It is not a, I originally saw it as kind of a punitive, but it's not really. The whole goal of it is to assist and aid us in getting back to where we once were. The chapter formed a couple years ago, and at that time, I recall we had a meeting with 70-some people in the room physically, which astounded me. But and then COVID just whacked the heck out of it, and we went down. We were not operating in a virtual world. And today we are really for the first time as a chapter, but we're also seeing light at the end of the tunnel to where we can come out of the houses, come out of the offices, and actually meet in spaces. Going back to what Noel was saying about the meetings every month on the third or fourth Thursday, we might envision that as being, yes, we need to have chapter meetings sometimes. We need to have topic specific things, like we have a speaker tonight, but maybe we'll just have a meeting that's just based upon what that speaker wants to tell us. And there's also the whole concept of social meetings, because we want to make sure we're giving you opportunities to meet and greet and bond and share ideas with other people in the field. So we see different things that can be done to make that happen. Next slide. Okay, why do we need this? Well, as I mentioned, COVID-19 hit us pretty hard. It really curtailed the meetings and any programs we had underway. We need to pick up on member engagement. and participation in particular. Like I said, we had a lot of people in the first meetings. We had some other people who were doing some cool stuff. We were attending conferences and other STEM events, um, but that was impacted as well with COVID. So we're looking to build the membership back up, get them engaged, get them doing good stuff, give them a reason why they want to participate, and hopefully um, come away with some good projects within the chapter. And then also challenges with chapter succession planning. You know, it surprised me a couple weeks ago, I guess, when Noel said, you know, I've been the treasurer for such and such a long time. And when he said that, I said, yeah, you know, I've been the president for a long time too. And during COVID, we did not have the opportunity to really run chapter elections and things like that. And so without the chapter member participation and the outreach going on, it was something we couldn't do. So we've been carrying those roles for the entire time. And even though it can be interesting doing that, it's probably at a point where somewhere we want to get some new blood in there, get some additional ideas, some thoughts coming in from out of the box. People maybe have other ideas on how to do this. Third thing, challenge. Well, yeah, let me go to the fourth thing. And because of COVID, we were not able to hold our four membership meetings and big annual membership meetings during the last year. We were able to do board of director meetings. We were good at that, but we were underperforming as a chapter, so as the other ones were as well. And the goals and requirements are all based on if you're an actively participating, meeting, kind of moving forward chapter, and we need to get back to that point. That brings us as to why we're doing relaunch. We had a meeting back on the 28th of September with the people from the national office from ISC Squared. And they're actually, they're the international office, I would imagine, but they also represent the North American region, which is what we are part of. And we talked to them about doing relaunches and what it would take. And they've established a timeline for us to follow. It's going to take several months, 6-7 months before it's all completed. But I wanted to lay that out. Next slide, Noel, I'm sorry. I wanted to lay that out so you guys can see that. We had the orientation meeting with the national people on the 28th. There's things such as startup meetings. We have some events which are targeted to occurring on the 30th of November, the 15th December, 30 December. And as you can see, it becomes very aggressive, very, in a perfect world, and we're still in COVID. So it's a question of how often we can really get the people, the membership together to go over some of this stuff with us. But we're doing the startup meeting. It's not really today. It'll probably occur during the month of November. And but we want to lay the groundwork tonight to let you know that, hey, this is what's happening. This is where we're going. Here are the things we need to do. And if anybody out there is looking to help participate in it, more the merrier. Okay. We want your ideas. But we are going to be going back. We're going to be looking at all the documents we had to generate in creating the chapter, the goals, the objectives, the bylaws, all that great stuff. Because when we did that, we were going off some template that ISC Squared gave us. And since that time, we've probably gotten a little bit smarter at it. And I know when we started the chapter, we started running with it, and there were some other things that we probably should have slowed down on and focused on some other areas, particularly member growth and member service. And so we're going to capture that, but we need to update some of our documents to get to that point. And then have the chapters review that, chapter members. And along the way, we're going to hold an officer election, probably towards the end of the year. So we have the people who can carry this thing forward. Now, I do know Noel will be around, and I will be around in our capacity as the former president, former treasurer. And, so we're there to advise. But hopefully we'll get this thing geared up and running. Well, the success plan, when we put that together, that's going to tell ISC squared, here's what we're going to do over the next several months as far as developing a service within the chapter. So that'll be something that we as a group determine, and should work out pretty well. Um, we'll have some stuff that we'll be going back and forth with ISC squared national as we develop that. And most likely, several of you and a lot of others within the chapter have been members of other associations, other professional chapters of associations. And you see how things are done differently there and how we do things differently. And that doesn't mean that we're not open to change. So, we're looking for good ideas. Okay, where will we do the relaunch? At this point, we're doing it virtual. Um, we're going to use this to try to expand the outreach because we can get to a larger audience, uh, such as our guest speaker today, who's sitting up in Kentucky, as he said. But, you know, not everybody is sitting in Huntsville, and not everyone can drop what they're doing and attend a meeting on any particular day of the week. So we understand that. So right now we're going to be doing virtual. However, we do need to move to physical, and in-person meetings are important. Like I said, it's that opportunity to bond, to meet each other face to face, do a little networking. That opens up for better, more robust discussions on issues um, or topics that are under discussion. Uh, Sometimes that can be pretty exciting. And um, in general, I just prefer it that way. Those meetings could take the form of, once again, a social meeting, a membership meeting, a presentation meeting, various things like that. And of course, if you're in the board of directors or you're chairing one of the work groups, we'd expect you to have participation in the board of director meetings, which presently we hold every 2 weeks, twice a month. Let me put it that way. Okay. Do note at the bottom of that whole idea that if we do when we do physical meetings, and which we expect, we're looking for November, December, that we will follow whatever the available and appropriate COVID-19 guidelines are at that point in time. You know, Noel, at your venue over there, do you mask up?
Yes, sir. It's still a Huntsville requirement.
Okay, that's right. Okay, so we'll follow whatever it is, and we'll try to make sure everybody stays safe. Okay. Now, how will we relaunch? This is always a tough one because I don't have a laid out plan for this because we're looking for to be able to bring in input from the people in the chapter, and also to respond to that and incorporate it all together. But basically, hard work, a chapter membership, and the leadership. All right. First and foremost, this chapter is not mine. It's not Noel's. Um, it's no one person's, no group of anybody other than it's the members chapter. Okay. And if it's going to flourish, then we need the input and the assistance from the membership to make that happen. Uh, if you envision, if you envision the chapter providing services to members or services to the community, or getting involved in other things and helping people who are pursuing ISC squared credentials, helping them understand how to get there, and maybe even leading work study groups. That takes participation by the members to do that. And so we really want to encourage that as much as we can. And I think once people get involved in that kind of thing, it'll take off. You know, I know there's a pent up demand. I sat down at National Cyber Summit a couple weeks ago and had a lot of people coming up. There was a lot of kids from college coming through saying how they had Security Plus currently and were looking for something more. And they were wondering what our chapter could do to assist them. And that is, of course, one of the things, one of the goals of ISC Squared National is to grow the number of certified people within the ISC squared umbrella. More to follow on that. And then what do we get from the national staff in order to help us do that? They are the ones who maintain the master mailing list for all of ISC squared. They do not provide a chunk of that to us. If we want to broadcast a meeting notice to all the ISC squared holders within northern Alabama, we need to go through them, and because they have that. And sometimes they can only distribute to the people who have said they're willing to take and accept emails. So it's kind of complex at their end, but internally here, we're trying to get a better handle on what our membership consists of. Okay, and I say that because when we started this, we said, "Hey, this is hey, everybody, come on into the big tent. We're holding the meeting. No formalities, nothing like that. We just needed to know your ISC squared number and your name and your email address, so we could, get your CPEs back out to you, things like that." But there is a member application format that ISC squared does use. And I believe that in order for us to get the database to where it needs to be, we're probably going to have each member go out to the website and just complete that form. And that'll populate the database for us so that we know who you are, how to reach you. We don't give the information out to anybody. It's just internal for our use, and it's secured. But that'll be another step. So we're going to have to overcome the limitations of the National's email address database and create something of our own. So, okay. That kind of wraps up what I had to say about the relaunch, other than it started. We want to have it done in April. It's very much akin to what we did during the original launch of the chapter. One of the big differences is that we are chartered already and approved by ISC Squared. We are also recognized as a nonprofit, and we are also registered with the state of Alabama. Those documents don't go away. They are still in place, and Noel had a lot to do with that. And so we're not having to redo those materials, which were time consuming. So we should be good. Okay. Like I said, my biggest pitch is, what can we do to grow the membership and get the membership involved, get them participating? So anybody have any questions on anything I've said there?
Hey,
I've got.
Chuck, we're going to have to ask for questions to be submitted for email.
Okay.
We are running out of time here, so I apologize for interrupting you on that, but we really do have to keep moving on here. For the time being, if you have any questions, make sure you send it out to Chuck or myself. You can find our email addresses on the chapter homepage, or send it to.
Can they send it to Connect?
Yes, to connect at isc2-huntsvillechapter.org. Real quick, we have right now our annual meeting that Chuck was talking about is scheduled for December 16th, and we will be doing that as a virtual voting method. So if we have any more questions and you want to get it answered in this meeting, make sure that you wait until after the presentation, and we'll make some additional time then for additional questions. Okay, moving on to Mr. Isaacs.
Good evening, everybody. Thank you for inviting me. My name's Tim Isaacs. I believe Noel put out a bio, so I'm not going to waste time going over that. I've spent about 40 years in nuclear power, from the nuclear Navy to commercial plants, design engineering technician, and spent about the last 12 to 13 years as cybersecurity, specifically in nuclear plants, but did some stuff in chemical, fuels, DOE. So I've been doing this part for a little while. Okay, so this is cybersecurity and advanced reactor designs. I wish we got into some real whiz bang technology, that's just not going to happen because there isn't any in nuclear. There's a lot of cool technology, but it's not have anything to do with information or OT. That's about the same as everywhere. I'm going to go into a little bit on the differences between the reactor that you'll see down the street right now and the advanced reactors that are coming online, the Gen 3 and 4s, like the Plant Vogel, and the advanced reactors like NuScale and all the other ones you're hearing about. We're not going to have time to talk about TerraPower and high temperature gas reactors and thorium reactors and all that stuff. But their safety aspects are going to be similar. Okay, so let me get started with this presentation. Oh, you're not allowed to share your presentation. Okay, that'll work. Noel can move through the slides. Okay, so I guess I am allowed to. No, hold on. I'm having technical difficulties now. Darn. Okay. All right. So this is a word from our sponsors. Basically, the DOE gives us money. We have to tell you that anything I say is not the words of the DOE, but they're not responsible for anything I say here. All right. Next slide. All right. NuScale Power. NuScale Power was formed about 2007 for the purpose of building a small modular reactor. The concept came from a couple of our founders who worked on the Department of Energy multi-application small light water reactor program. I'm going to try to run through this as quick as I can. Fluor's a major nuclear engineering and project company. They came on board back about 10 years ago. The DOE's given us over 400 million, and I think we're due to get some more. We got about 600 patents now pending or granted. We're a relatively small company, 400 employees in 5 offices. The projections are amazing that if once we actually start deploying these things, when we have 10 or 12 out there, we might have 20,000 employees. That's just amazing to me, but it'll take a lot of folks on the ground to build these things. The U.S. Regulatory Commission approved our design. So all these other ones you hear that are going to be built next year, not a single one of them has an approved design any place in the world. It hasn't happened yet. The Chinese don't bother to approve designs. They just go ahead and build them. Total investment greater than 1.2 billion. That was the number a little while ago. It's probably more now. People are coming on board all the time. Next slide, please. All right, that's our mission. Advanced reactors, smarter, cleaner, safer, and more cost competitive. We'll have a slide down the road here. It'll show how much safer than that reactor down the road NuScale is. Next. Okay, that's the core to us right there, that thing. It's about the size of, it's about 2 buses long and about 2 buses stacked together. That's the size of it. It's a one package. It's got a reactor down in the bottom, integral containment, basically no pipes, no motors. It's all passive, at least the heat generating and reactor part is. Again, we're going to move along through this. We'll talk about this stuff again. You can scale it up anywhere from from 4 to 12 modules. Theoretically, you could have one, but that wouldn't be very cost effective. Each module puts out about 72 megawatts electrical. That runs about 300 thermal megawatts. Next. Okay, this is the reactor down the road. Let me get can I get my giant pointer on? Yeah, I can. My giant pointer shows up on this screen. All right. So nuclear reactors 101. You got uranium, and in all the reactors today, it's uranium in a core in both types. It's the boiling water reactor, pressurized water reactor. Gets hot. Water circulates around the core to move that heat out. In a pressurized water reactor, that goes through a steam generator where it runs through some tubes in the steam generator, and the secondary plant water is fed into it, gets heated up, turns into steam, goes out, spins a turbine, which makes electricity, gets recondensed in a condenser, gets pumped back in as feed water and starts to cycle over again on the secondary side. That steam cools off the primary, gets sucked into the suction of a reactor coolant pump and shot back into the core where it comes up through the bottom and keeps the core at cool or nominal operating temperature reactors have what they call T hot and T cold. I had a supervisor when I first got out of the Navy working on these plants, and I was supposed to replace a T cold thermometer while the reactor was operating. And I'm like piling up sheets of material. And he goes, "What's that for?" I said, "It's to insulate so I can work on the wires." He goes, "Oh, you don't have to worry about that. It's the cold leg." Okay, the hot leg is 570 degrees. The cold leg is 530. Believe me, the cold leg at an operating reactor is plenty hot. Boiling water reactor, they operate at lower pressure, so the water turns into steam, goes out to a turbine, makes electricity, gets pumped back in. They don't have reactor coolant pumps. They have what they call circulating water pumps. That keeps the primary fluid, which is the working fluid. It's the same that goes out and makes steam, moving around in the secondary. Otherwise, it would just kind of pool there. Both types of plants have lots of pumps on the outside of the plant, high pressure and low pressure fill pumps, safety ejection pumps. They have core cooling pumps that on some plants spray water right into the top of the reactor. And all of that stuff has nothing to do with making power. They're all huge pumps, 480 or larger motors, usually 50 to 2,000 horsepower. And their only job is to sit there in case of an accident. Both plants are very similar for that. Boiling water plants have stuff inside of their containment that does other stuff. We're not going to get into those differences. It's just way too long. Okay, so move on next slide. Okay, our NuScale Power module, like I said, it's all in one place. One of the things this plant does not have, it has no piping in for the primary coolant. What you have is you have a reactor vessel. Inside of the reactor vessel is the core at the bottom. On top of the core, it's kind of like a chimney. So as the water heats up, it goes up this chimney, reaches the top, flows out. This very top here is our pressurizer. It's inside of the reactor vessel. Flows out the top of the chimney, and these little checkery things in here, I can't see them very well on this view, but that's our steam generators. Those are inside also. The steam generators are inside the reactor vessel. So as the water flows down, the secondary water is piped into the steam generator at the bottom. The cools off the hot water from the reactor that flew up here. As it cools, what does it do? It gets dense, falls back down, heats back up. So there's a constant cycle. The steam comes out of the steam generator, goes out, spins a turbine, gets pumped back in, just like it does in any other plant. There is no difference in the secondary plant for a NuScale plant, except it's much smaller. Instead of having one big giant turbine almost 1,000 feet long, we have a bunch of little turbines that would fit in your garage. One difference there is one of those 1,000-foot long turbines costs approximately $600 million and has a lead time of 5 to 20 years. Literally, nobody makes the darn things anymore. There's only 2 producers in the world for those 1,000 megawatt turbines. You can buy a 72 megawatt turbine. Well, you can't go down to your corner Lowe's, but you can order them with about a 1-year lead time. Okay, so let's go on to the next slide. This is another picture to show a comparison. So here's a NuScale Power module. There's a steam generator in a regular plant. NuScale Power module is about the size of a steam generator. This is showing one side of, this would be a 10 module plant or a 12 module plant. And so what you see here is it all fits in a big old swimming pool. That's our ultimate heat sink. That swimming pool is located below grade level. It's underground in a building that is similar to this containment structure. In other words, it's rated for earthquakes and aircraft impacts. Basically, they're designed to take, I believe they tested them by flying a Phantom. There's a video somewhere on YouTube you can find where they put a Phantom jet on a rocket sled, flew it into the containment building at like 600 miles an hour. And that was a 1/4 scale containment building, built to similar standards. That building's not going to come apart. What you saw at Fukushima cannot happen at even a modern regular nuclear power plant. Okay, next slide. Okay, we talked about how the NuScale cycle works. So again, water gets hot, goes up to the top, falls down through the steam generator where it meets the secondary water, which gets hot, goes out and makes steam. That's our regular cycle. In the event that we have to shut down the reactor, we would use, just as plants today do. Plants use their steam generators and their secondary plant to take that steam off, condense it, and pump it back in to remove heat. That's a normal way to remove heat in any plant while you have it available. That'll cool the plant down to about 250 degrees. Then you have to do something else. You have to do some kind of forced cooling. At NuScale, we at that point we'd switch over to our decay heat removal, which are outside of the reactor vessel and containment and inside of the pool, and again flows by natural circulation. The water flows up through the generator, through the top, and instead of going out to the steam plant, it falls down through goes up through the heat exchangers. All of that heat's contained in the pool. During accident scenarios, we have other ways of cooling it so that works fine. And this is all no pumps, no valves, no external sources of water. We also have what we call reactor recirculation valves for extremely long-term cooling, where we flood the containment. This containment and the reactor vessel normally operate at a vacuum. For long-term cooling and with no operator action, these valves here will open, it'll fill up, and we'll lose water, heat just through convection through the walls of the containment vessel to the pool. That's our long-term cooling. Okay, next slide. I'm rushing this a bit because I think we're short on time. Okay, basic nuclear safety. This is going to be the same for every whether it's a pebble bed reactor, a thorium reactor, advanced reactor, or the reactors that were built back in the 1960s and still operating today. Okay, nuclear fuel is contained in some kind of assembly. Most plants, that's a pellet. The pellet's the size of a joint on your finger, approximately. They're about maybe a ½ inch wide, almost an inch long. There's hundreds of them in a fuel rod. That fuel rod is made in most reactors of stainless steel. Sometimes in some plants are a little bit more advanced materials. The Navy uses something completely different, but it's still similar. So that's the first line of defense. That stainless steel is our first barrier, because the whole purpose of safety in a nuclear reactor is keep the nastiness, and there is some extreme nastiness created by fission. There is stuff created by fission that is so radioactive it'll kill you almost instantly. I don't know, have any of you ever seen Cherenkov radiation? Cherenkov radiation is when you see a picture of a nuclear power plant, when they look down where the core is, that blue glow. If you tried to swim to the blue glow anywhere, you would die at about the time you got to it. Literally, it takes a lot of radiation to make a blue glow. Okay, so we have those. Those are all stacked together in a fuel assembly. Those stacked fuel assemblies are bundled together into a core. In the fuel assembly, there's a control rod. What the control rod does is controls the reaction. Normally, it's operated almost completely out of the reactor. Something happens, it falls in by gravity on a pressurized water reactor, and it's got poisons. It absorbs neutrons, makes them not available for the reaction. On a boiling water reactor, they come in through the bottom, and they either use compressed air, huge springs, and sometimes explosive squibs to get them moving. So the next layer of protection is the primary coolant system or reactor coolant system. That's all the pipes, the reactor coolant pumps, the insides of the steam generator, the reactor vessel, and the pressurizer. There are literally in a modern nuclear power plant tens of thousands of square feet of piping and vessels. And in a pressurized water reactor, that has to operate at up to approximately 3,000 pounds. Boiling water reactor is about 1,500 pounds. And to keep all that in, because that's a job. I mean, those pipes are 16 to 20 inches thick, the large ones, wide, and they're literally 5 inches thick. That's a lot of steel, a lot of weight. So just in case something there breaks, you put it into a big old containment vessel. Most containments at the bottom are about 12 to 15 feet thick, and up at the top are about 4 feet thick, made out of reinforced stress concrete with a steel liner. That's a lot of stuff to keep your nastiness inside. And by the way, it works. 3 Mile Island, not a thing got out of this stuff. Even in 3 Mile Island, the reactor coolant system was not breached. They did vent some stuff off, but for the most part, did its job. But okay, next slide. So that's how we keep the stuff safe. New generation reactors, AP1000 similars, and boiling water reactors, EBWRs. They operate with passive safety features. So all the pumps that those plants need to keep things in there, the high pressure safety injection pumps, spray pumps, the newer plants don't need them, or at least don't need them for the first 72 hours. And reactors are different from any other plant because when you turn a reactor off, it keeps on producing heat. Most plants, your natural gas plant down the road, when you turn it off, when you shut off the fuel supply, it starts cooling down immediately. 1,000 megawatt electrical reactors, 3,000 thermal megawatts. Right after you shut it down, it'll put out about 300 megawatts. And that'll follow a decay curve until it'll be just a fraction of a percent a couple of days later. But that heat's got to go. 300 megawatts of heat is a lot of heat. It's enough to drive an aircraft carrier at about 40 miles an hour through the ocean, just for example. About 400,000 horsepower. Advanced reactors move forward these trends. They eliminate the lead for power and operator actions. The AP1000 plant I worked at, the operators could leave for the initial 72-hour period and everything would be just fine. And that's if all the power to the plant went away. Everything fails in a safe direction, either by solenoid valves that open, sometimes with squibs that when you take power off, they fire and move a valve. NuScale plants use all those same features. As a matter of fact, NuScale plant is not a Gen 4 plant. It's an advanced reactor. We're an advanced reactor because we get rid of that piping. And I'll show you on a little slide coming up why that's the case. Next. Okay, so this is your reactor down the street for a pressurized water reactor. This is your reactor down the street. What this shows you is risk, frequency times consequences. And how we recognize plant risk is how many times we have an accident that basically can release radioactivity at a dangerous level to the surrounding community. How many reactor years per incident? And it's shown as, a 10 to the minus. So for your operating plants today, it's 10 to the minus 5, about 10,000 years. So for each plant, once every 10,000 years, so 10,000 years per plant per incidence. Now, when you have 2,000 plants, what does that mean? That means every 5 or 6 years, you're going to have an incident. Modern boiling water reactors, about the same. The new light water reactors, AP1000s and boiling water reactors, they take that up by an order of magnitude. So they go from 5,000 to maybe 30,000 years. A little bit better for the boilers. This is a NuScale plant. NuScale plant, using the same analysis, is one failure per every 3 billion reactor years of operation. That's several orders of magnitude better. And that's because like this, like I said, there it is. We got our nastiness inside of the reactor vessel, inside of the containment, inside of a pool, inside of a steel cage, steel and concrete liner, underground, covered up by a containment building that can take a magnitude 9 earthquake or a direct hit from a 747. The bioshield's kind of it's important if you work there, not so important for everything else. Okay, one of the fallbacks from this is all nuclear power plants have what we call an emergency planning zone. The emergency planning zone, if you've ever been near a nuclear power plant or even a chemical plant, you'll see sirens everywhere. For most nuclear power plants, and it's based on the design of the plant, weather conditions, a lot of things go into it, but the standard is 10 miles in radius. And then they have a management planning zone that runs 50 miles in radius. You could put approximately 20,000 NuScale plant emergency planning zones inside of the emergency planning zone for a regular reactor. The NuScale emergency planning zone is approximately 40 acres. It is the footprint of the plant. Okay. And it should follow that the other advanced reactors would be similar. They're striving for the same thing. Next slide. All right, I'm not really going to go over this. We talked about it already and we're short on time. It kind of shows what the power does over the length of time. So, 10 megawatts immediately, then 2 after an hour, 1 after a day, 0.8. It's a curve. After 30 days, it's 400 kilowatts, and it gets real small in long term. It's a regular decay curve. Okay, let's go to the next slide. Okay, these are components needed to protect the core. We're only going to stay on this second. I'm not going to read them all. The stuff you can barely read here, this is what's in a conventional plant today. This is what NuScale needs. In a regular plant, all of these systems have electric motors and switchgear. A lot of them have control systems. Modern electric motors and switchgear are digitally controlled. Matter of fact, modern electric switchgear has a server that would rival anything in one of your, maybe not one of your blade servers, but it has a pretty powerful server. It's not run by a Pentium processor. It's pretty decent server that runs the electrical switchgear, and all the breakers are smart. They're tied together by a network system. So they all have that. Now this is NuScale, the dark ones. The only thing we have with any real digital components in it is a reactor protection system, and we build that out of a programmable grid array so that you can't reprogram it if you want. You have to ship it back to the factory. There is some tunable stuff in there, and we have to take measures to protect that. But the actual stuff that shuts down the plant if something goes wrong, it's an FPGA or similar technology. Next slide. Okay, now I'm going to do the basics. Operational technology in nuke plants. I don't know how many folks work with operational technology, but operational technology is similar to information technology, although we have a different focus. In operational technology, availability is the be all and end all. Operational technology systems have to operate 24 hours a day, not 23.999. They have to operate all the time. They cannot shut down except when planned. When operational technology systems shut down badly, bad things happen. Refineries explode, people die. The other thing we care about in IT is integrity. Our data has to be accurate. Confidentiality is not really a concern. And I mean, it's not that we don't care. It's not really a concern. Nowhere near what the availability and integrity is. So all modern plants, even the refinery down the road, they all use a defense in depth. I don't know how hard they do it. In nuclear plant level 4, that's our protection systems. That's what protects the reactor core and initiates any emergency safety functions. That's a completely separate system from the level 3 systems that operate all the pumps and valves in the steam plant. Those are isolated. The only way data gets out of here is through a data diode. No firewall, it's regulatory. Can't do it. It's either it doesn't get out or it's a data diode, or it can come out analog. A lot of plants still do that. So in other words, they use analog symbols to get that information out. Level 3 is our control system. Again, should be one-way transfer. Most plants, that's a data diode. In some plants, they do use a firewall and a DMZ because they may have a little bit more dependency with level 2, which we call our plant network. Plant network is where we might have procedures. Oh, shut up. Sorry about that, folks. I thought I turned the darn thing off. We might have a procedure system. We might have our engineering drawings. There might be a lot of stuff in there that you use on the plant all the time. That is probably hooked up through to the business LAN at level 1. And then the outside world, the wide area network or the internet's level 0. You guys are all familiar with this, same thing where we at. We're just a little bit pickier about how this information gets out between layer 4 and layer 3. Modern plants are highly automated. This is the NuScale control room for a 12-unit plant. We have gotten permission, a 12-unit plant in even an advanced, like an AP1000 plant, would require approximately 18 operators. We have permission. We went through it with the NRC. We could operate a 12-unit plant with 6 operators. They're that highly automated. Plus the fact that they fail safe is a pretty good thing. Our operators can all leave and everything will be just fine, not only for 72 hours, but forever. Next slide. All right, cybersecurity with nuclear plants, regulatory compliance. Problem with nuclear plant is it's the law. You don't have a choice. It's worse than Sarbanes-Oxley. They're some of the most regulated sites in the world based on federal, state, and local law and codes. The primary regulatory body is the U.S. Nuclear Regulatory Commission. That the U.S. Nuclear Regulatory Commission has what we call the Cyber Rule 10 CFR 73.54, requires protection of computer and data facilities at nuclear power plants. There's other regulations that the NRC has that do it, but that's the main driver. They're implemented. They use regulatory guides published by the NRC or NRC accepted industry guidance for cybersecurity architecture. There are two accepted ones. One is from the Nuclear Electric Institute, and one is from the NRC. That guidance is the only architecture that you're allowed to use. You can't make something up on your own. It has to meet all those requirements. The electrical generation of distribution nuclear plants is also regulated under the Federal Energy Commission, FERC. Back in about 2011, they got together and it was just too big of a hassle. So basically, FERC turned over everything from what we call the intertie breaker, where you tie to the bulk electrical grid or the bulk electrical supply. Everything inside of that is under the purview of the NRC, because FERC looked at the NRC's requirements and they were much more rigid than the FERC requirements. So basically, at the plant, we don't deal with FERC. The utility deals with FERC. Next slide. Okay, regulatory compliance. We're also subject to all the other workplace and other regulations for any industrial facility or any facility, some of which may include cybersecurity requirements that aren't addressed in the rule. There are cybersecurity requirements for your environmental monitoring, for your industrial discharge, all kinds of that stuff. We still have to meet all those too. Basically, the nuclear powers are digitally controlled and they're expensive. Okay, a $2 billion plant that's controlled by digital equipment, highly networked. If you ignore that, except for the regulatory requirements, you're putting an awful big risk out there for your company. That just doesn't make sense. And people shouldn't do it. One of the things is successful attack on any nuclear facility would cause great harm to public confidence. You know how it sounds. If anybody's heard about anything that ever happens in a nuclear plant, or even maybe your local refinery where it's not a big deal and it doesn't blow up, the news person always says, and the utility says that the public is not at risk. And you know that they're saying, well, they're saying that, but you know it's not true. So we don't want that to happen. Keywords in nuclear power: safety, which is safety systems, shut down and keep the plant shut down. Security, physical security of the plant. In other words, all the cameras, badging, motion detectors, everything about physical security. Emergency preparedness are those things that allow you to deal with an emergency after it happens. Communication systems, monitoring for the emergency preparedness, people on and off site. That are the clue for nuclear power. Those are the things that we are regulatory by the NRC required to protect. I'm doing this without my notes, by the way. Next slide. By you running the slideshow, I cannot see my notes. Okay, like I said, allowable architecture set by regulation. Cybersecurity program of nuclear plants follows the same path. You set policy and select the architecture. You get two to select from. A little easier than when you're setting it up in the IT world. You got lots of architectures to select from, but they all do the same thing in the end. You identify the assets protected. Same thing you got to do. We have a rigid rule for how you do that. Currently, there's a change in progress. What you do is identify the critical systems, those that have that safety, security, emergency preparedness function. Then every digital device in those systems is called a critical digital asset. It's in a critical system, it's digital, it's a critical digital asset. Then you analyze and apply security controls. The way that the controls work, they're basically pulled, if you're familiar with NIST SP 800-53, our controls are a tailored set of those. Pretty much follows right down the rule, and every bullet in those controls is considered by the regulators to be a separate control. Ends up with about 580 controls, 5,000 or 6,000 devices, separate analysis for each control, millions of data points. Average cost is about $17 million per plant, just to assess and get the program in place. In general, controls are binary in a regulatory environment. The NRC is, if the device can do a control, it must be a control. Even if it's something that's locked up in a room that no human can access, you have to apply the control. we're working on that. That's one of the things that's changing. Next slide. We're also faced with all the same challenges LT faces in every facility. Updates are hard to perform, especially in nuclear plants. Most legacy nuclear plants have obsolete things. You will find Windows 3.0 in nuclear plants running control systems. Because the control systems last for 40 years, unfortunately, the vendor quit making it, so they don't update the software, and the new software won't work with the old system, so they're stuck with what they got. And the software they have won't run on newer operating systems, and then you run into a problem of, I've done it where I've slowed clocked and all that kind of stuff. Unfortunately, you can't test it enough as a private entity to do that. It's just, you have to test it way too much. So SCADA, systems for control and data acquisition. So updates require outages. You got to shut the plant down or part of the plant down to get to that control equipment. Again, equipment's obsolete and off supported. That is an OT problem everywhere. It's just, it's a big deal to put in a control system. It's not just putting in a new computer. Next slide. OT equipment can be very sensitive to scanning for IT systems. So a lot of the scanning tools you use in an IT system can take an OT system offline. Controllers are stupid. The heart of an of a control system is a programmable logic controller. It's a great device at what it does, but it's stupid. And a bunch of communications come at it that it's not used to seeing. It'll just quit working. So now the newer systems, that's better, but older systems, very sensitive. Basically, if the vendor of the system doesn't approve its use, don't use it. OT control, especially safety systems, they got to be available all the time. We already said that. Proprietary protocols are a real problem. In nuclear, they're not so big a problem because they're pretty much verboten. If you have to use a proprietary protocol, you have to take all kinds of steps to ensure that it can't hurt anything. In my other slide, so I said, so if you have an event, just turn it off. That doesn't work in an OSIS system. If you just turn it off in a chemical plant, you're going to blow something up. In a reactor plant, you're going to, at a minimum, cause a loss of output. You can hurt people. You can break things. So incident response planning is much more difficult. Incident response planning for how to, in the event of a cyber incident, requires operators, engineers, licensing experts, emergency preparedness, and physical security folks. It's a big deal. It's hard. That's why most plants don't do it. I mean, they have very little. Basically, they pray it never happens. Next slide. Okay, cybersecurity for advanced nuclear plants. We're going to move forward. Okay, the nuclear industry has responded to the burden of these huge numbers of critical digital assets by simplifying and quantifying the process. The NRC has accepted a new version of the guide for how to get these critical digital assets that basically says, okay, you still have to identify your critical systems, but inside of them, if that device doesn't have a function that is safety, security, emergency preparedness, and doesn't support a function. In other words, your HVAC units might still be under the cyber rule because without them, your protection system doesn't work. So that's dropped the numbers from thousands to hundreds, maybe. So from 5,000 in Vogel, it dropped us to about 1,000. We're hoping that they actually apply it there. Okay, advanced power plants have far fewer systems that have an SSCP function. At NuScale, we only have like 3 or 4. That's it. We don't need power. We don't need support functions. And the reduction is due to passive safety features. So it wasn't any increase in OT capabilities or in computer science or anything else that allowed us to simplify our cybersecurity stance. It's the mechanical, thermal hydraulic, nuclear design, and civil engineering design of these plants that allows us to, that makes them inherently safe. But that makes my life a lot easier. Electric Power Research Institute, EPRI, they've produced an assessment method. They produced it for nuclear plants, but if any of you look it up, you can go look it up. It's called the TAM, the Technical Assessment Method. You want to take a look at it. Those of you who are using pretty much cutting edge, risk-based security assessments for your components, you're going to recognize it. It looks pretty much exactly the same. It's a risk-based approach, so it gets rid of that binary control application. We feed in all the data that we would need to do that control thing. We run it through we take a look at attack surfaces and exploit mechanisms. And out of that, we come up with a security ranking compared to the inbuilt security features of the system. And we get basically, we have a risk assigned. In other words, if the risk is greater than X, if we're less than that, we don't have to apply any controls. If we're greater than, if we have some residual risk, we apply controls to the risk until it's less than the allowable risk, and ta-da, we're done. So we don't have to apply a bunch of controls to things that don't need them. We're hoping that the NRC lets us get away with this. It looks good. Vogel's the first plant to try it, and several large operators have signaled to the NRC they want to move to it. It's a lot of work up front. It's a lot harder because you have to know a lot about the equipment, but you were supposed to know about that in the old one too. Just a lot of people didn't. Next slide. Here's the other thing: cybersecurity by design. Modern plants that are out there right now, the existing plants, cybersecurity was not a thing in the OT world until the late 90s. Nobody even thought about it. As a matter of fact, I was one of those guys when I was in design engineering. When cybersecurity started sniffing around about 97, I basically said, get your camel's nose out from underneath my tent. I don't have to worry about that. I'm air gap. Nothing can hurt me. We kind of know that's not true now. But I was one of those guys, so I understand their point of view. So we have cybersecurity design that includes it from the beginning to the end, all phases of design and acquisition. We don't have anything to do with operation of the plant unless the customer hires us to operate. We've adopted a revised version that was talking about NEI 1004. That's that where only the things that apply get that are critical assets. We don't even call them critical digital assets because we want to avoid that term. I'm still hoping we're going to get away with that too. Then we have planning. So we plan system assessment planning to make sure only those that have SSCP functions, we group them together. I don't have to have a separate assessment for 3 brands of PLC if they share attack surfaces and exploit methods. I'll have one assessment for that. So it's a lot of work up front to get those groups organized. But once I do it, I'm looking at, I think, for an entire nuclear plant, approximately 200 assessments. I'm still guessing a little bit, but I think I can do it with 200 and maybe far less. I'm hoping to get the cost of assessing this plant the first time down to around $2 to $3 million. If I can pull that off, subsequent plants, they're all going to be the same almost. We'll be in the hundreds of thousands of dollar range. Huge saving for the customer. The other thing the TAM does by using this risk-based method, get a vulnerability that pops up or a threat, we plug it into the calculation, see if we need to apply controls. We don't have to reassess everything. We'll have it sitting there. We have a tool that we think is going to work. Poor Vogel paid lots of money to sharpen it, and we're hoping to get and use that. And if not, I know how to develop tools. Next slide. So I just talked about risk-based process and why it's good. So I kind of got ahead of myself there. That mirrors what you guys are doing now, right? Those are you guys that are applying risk-based security management. So we're just doing the same thing in OT, and this is moving into the oil and gas industry. They like it, and they're starting to grab it. And by the way, nuclear's tough. Chemical's harder. The cybersecurity regulations on chemical plants are actually harder to comply with. I don't know if it's because the regulators just don't do as much. Luckily, the guys that work for the NRC tend to be nuclear engineers, and they're kind of smart. Maybe not smart enough to live in Huntsville. I know you guys are the smartest city in the world, but they're pretty smart. That's why you don't try to pull the wool over their eyes. It doesn't work. And if they catch you, you get to go to jail. So you should be familiar with this risk-based approach and how to apply it. Next slide. Okay, advances in reactor plant design. Like I said, it's not the advances in digital technology, computers and programming, or even the advances in cybersecurity that makes them safer. What makes the plant safer is that just the basic mechanical and engineering design. Still, no matter what, it's not an option. It's the law. We got to do it. It's difficult and resource intensive, but we are working towards a way to make it easier and somewhat automated. In other words, we have a tool, we put the input into the tool, which we hopefully get from the vendors. We're trying to get our suppliers to fill out our data sheets for us, and that gives us the information we feed into the TAM. Next slide. So by designing in cybersecurity, we can meet them efficiently and to the extent that technology allows for the platform. I'm not trying to come and retrofit network taps. We're building that in. I'm either going to have network taps or I'm going to have span ports. We're going to monitor our networks 100% real time. Every bit that goes through my network is going to get analyzed. I'm going to know when one piece steps out of line. Just like you do on your high requirement networks, it's going to be the same thing for an OT network. There's no reason not to. Tools are there. It can be done. One of the things is I kind of have a no vote. If that vendor can't supply that kind of look into their system, we're not going to buy their stuff. We'll buy somebody else's. There's plenty of people out there that sell control equipment. Vulnerability management and updates can be automated, like you said, and even centrally managed to an extent. With our requirements for data diodes, that's a little harder. SneakerNet's still the rule, and you're going to have to do some zero trust to make sure you don't SneakerNet anything in. But again, zero trust is the rule. Use risk-based approach. We already talked about that. Next slide. Challenges for nuclear power plants and everybody. The Internet of Things. The Internet of Things may seem wonderful, but it is disastrously dangerous in OT. It can be introduced unknowingly. Sly War Story is doing a walk down a plant Vogel, big old huge valve. Somebody says, hey, this thing says Bluetooth on it. Well, wireless is not allowable in nuclear power plants unless it meets very strict criteria. It's not that it's not allowable. It's just you can't use it certain places, and there's lots of rules. This thing was out where anybody walking through the plant, basically walking through the parking lot, which is anybody, could access it. If the plant was operating, they could shut off all the cooling. Wouldn't hurt the plant nuclear wise, but it would shut down 1,300 megawatts of electricity, about like that. And you could do it with your cell phone. And it could have infected the rest of the system if you'd have been smart enough to do it because it was networked. All right, the evolution of persistent threats, introducing malware and malicious hardware in the supply chain. In my notes, I don't know if any of you guys remember a few years ago, Dell computer motherboards. Thing looked like a grain of rice laying alongside of one of the network support chips. It was actually a monitoring chip that was installed in China to spy and allow for the insertion of malware at some given future time. I was working at the DOE at the time. We had to take every single Dell computer we had apart and inspect for that, which meant I had to remove CPUs because you had to look under the CPUs to make sure there was nothing there. It was a pain. And that's not going to get better. Configuration management of thousands of devices. I mean, that's the IoT, making sure that nothing in the supply chain comes in. Nuclear actually has an advantage in this realm. We're kind of required to keep a really close tag on everything that goes into a plant. It's a lot more painstaking, but we're already doing it. So all we have to do is leverage that into our cybersecurity and learn the lesson from Stuxnet. Okay. We got to learn the lesson from Stuxnet. The most secure OT system on the planet, literally buried in a cave, air gapped, was virtually, literally destroyed. Not the system. I'm sure that the controllers and the network was working just fine, but hundreds of millions of dollars worth of centrifuges were completely destroyed by detailed knowledge of the OT system and social engineering. And this isn't hard. Let me tell you how this could happen. I worked as a design engineer. I decided to put on my brag sheet for the plant I'm working on. Hey, I just installed a Siemens 3200 system to control my main turbine, and I saved 400 man hours and $1.2 million in equipment costs by bringing it in 3 months under budget. Well, I just told everybody in the world what's controlling my main turbine. I can go on eBay and buy a Siemens controller for a couple of $100. The challenging part is I got to find somebody. I got to go up on the web and buy an illegal copy of the software and get around the license protection. Now I have got an engineering tool to hack that thing, and I can do anything I want to it. I'm not a hacker, and I know how to get into that stuff. If I'm a nation state, so the lesson from Stuxnet, don't brag about it. Treat your OT knowledge And actually, IT systems are the same. You don't need to tell everybody what's in your system, and you don't. And so OT has to do the same thing, but we're not good at that. We brag about what's in our plants. Supply chain and advanced persistent sets. Everybody knows about that. Solar winds and others all the time, and we're going to see these more and more because they're lurking, and we don't know when they're going to pop up. And this is the real threat for OT and nuclear plants. Like I said, we're air gapped. You're not bringing anything into my system from the internet. It's just not happening. You can't do it. But somebody walking in with a laptop from a vendor could, and a patch published by a reliable supplier of security software that I go and install can take out my plant. Next slide. Adversaries are focusing on IT. I went to the ICS conference, which is an OT cybersecurity conference in 2015. The head of the critical infrastructure branch of cybersecurity of the Homeland Security was talking, and they run honeypots. Homeland Security in cooperation with a couple of large security firms. They run honeypots all the time. And at the time, they put up OT honeypots in the United States, utilities, oil and gas refineries, chemical plants. And they kind of weren't paid attention to very much because at the time, adversaries were focusing on the Middle East. They put up Israeli and Saudi OT facilities, and they would draw lots of attention. But at the time, only about 10% of the attention was focused on the OT. People that did go to OT things were looking for industrial knowledge. Corporate knowledge. They wanted credit card numbers. They wanted PII. They wanted the kind of stuff that any hacker wants when he raids a business. That's changed. In the last 2 years, the honeypots are drawing attention to the OT side. They're trying to get into the control systems and figure out how to get them because they've realized that, like with Norsk Hydro and the Russian-Ukrainian attack, there's a big thing of money. If I can turn off power to the eastern United States, how much are you going to pay to get it back? And I can turn it off, and I'm not that brilliant. So imagine what a nation-state actor can do. So it's that's a big deal. Final point: most significant challenge for OT anywhere. In nuclear, it's even worse. People. I've worked with the assessment teams. A lot of them were good folks. Most of them didn't know anything. Either didn't know anything about OT or didn't know anything about IT. And very few of them were very knowledgeable on cybersecurity. They were engineers and technicians that had worked on the equipment. Not the right people to be assessing, but it's what they had. OT requires personnel with skills that include an understanding of what the systems do, because you got to understand it, and how they relate to the operation of safety, process, plant workers, and public. That's an enhanced skill set from the IT cybersecurity professional. It is not a different skill set. It's an enhanced skill set. Nuclear cybersecurity professionals also have to understand licensing issues. At least some of them do, because the licenses are a rule of law. How it works with the Nuclear Regulatory Commission is your cybersecurity program or is part of your licensing document. And basically, the Nuclear Regulatory Commission is kind of like the Khan was in running his empire. You make your laws and you shall follow your laws. If you don't follow your laws, we'll kill you all. That's pretty much it. So the Nuclear Regulatory Commission lets you make up your rules. They review them. If they approve them, you will live by them. So you need to understand that license because it dips into everything and how they relate. Next slide. Okay, I rushed through that because I knew we were short on time. I probably drug us a little long. Now it's time for questions. So I can take a breath while you guys figure out what you want to ask me. War stories, whatever.
So I'll ask a really quick one. So a handful of us on this call deal with RMF accreditations. I might have skipped over this, but do you guys go through similar accreditations? What used to be DICAP, what might now be RMF, things along those lines?
Each site is required to qualify their cybersecurity personnel. It's pretty limited. I mean, I was a member of ISC squared. I'm not by the canons. I'm not allowed to talk about what I used to have, so I can't. I'm a CISM, Security Plus, lots of other certifications, but in general, those people are not certified. So it's a local qualification process that, depending on the local qualification process, might be very rigid, or it might just mean he breathes and he can get in the plant. That's part of the license, by the way. So it's part of your security program.
So I guess that answers the questions about personnel, but I guess when it comes to the systems themselves, are there not certifications, but accreditations or authorizations
Well, there's
for those kinds of systems?
Nuclear stuff that does a safety purpose has an N stamp. It's covered by a 10 CFR 5049 Part 21, I believe is what it is. That's very specific, and you have to meet a lot of things. It's more for non-digital stuff, but things that have a safety function are there's not a certification per se for those digital things, but the list of requirements, it's an IEEE requirement, and I don't have it on the top of my tongue right now for digital safety systems. But there's an IEEE requirement they have to meet, and it's pretty dang detailed. So the vendor certifies they meet that.
Okay, cool. Thank you.
Got a question here from Jason Sumner. It says, since it is up to the local site to implement the cybersecurity posture, there is not a third-party external entity that assesses the security?
Well, there is, because the nuclear industry has what we call INPO, Institute of Nuclear Power Operations, which is a semi-regulatory body that was instituted after 3 Mile Island to share experience, learning. So we do self-assessments. Cybersecurity is kind of lagging on that. Realize that the nuclear power plants were originally required to have their initial assessments and cybersecurity programs in place by 2012. That was extended till the end of 2017. And that's for the initial assessments. There's only been, I think, about 15% of the plants have been inspected by the Nuclear Regulatory Commission. Now, that is the final third party that comes in. The Nuclear Regulatory Commission has an inspection guide. By the way, it's on their website. You can look for the cybersecurity inspection guide. It's available, just like all the licenses for the plants. And when you dig into their licensing documents, you can read their cybersecurity plan. So the Nuclear Regulatory Commission is that third party that comes in and tells you you're in trouble. But INPO is stepping up a role, and plants tend to peer assist. There's some other smaller bodies where plants have grouped together for mutual assistance, and we come and inspect each other. And one of the things I do, I'm a certified information systems auditor. I've run those for a number of plants, but it's probably a decent business opportunity if somebody could get some people who had the knowledge together to provide that.
So one thing you mentioned, the initial assessment for the power plant coming in at something like 12 million, and then you were hoping to get it down to $2 or $3 million dollars for that assessment. So when I heard you talk about that, I assumed that was your third-party assessment that you were talking about.
No, that's actually the assessment of the components. In other words, taking a look at all your components and putting them into a risk-based analysis, and what kind of controls do you have to apply. And then the expensive part of that is putting it in writing for the NRC. Everything has to be written down, has to be documented. That's the fun part. And I have to have evidence. So I need vendor documentation. We may even have to ask vendors to break into their code a bit. We need to get pretty deep into it for some of this stuff. But luckily, the biggest part of that is minimizing the number of things I have to do that to. For the rest of the plant that's not under the NRC's rail, I'm going to use NIST SP 800 82, which is Industrial Control System Cybersecurity. It is again taken from NIST SP 800 53 and tailored for control systems, and apply that. But since I don't have to do it, I can be a little looser in all of the documentation required. I can automate most of that.
It struck me in particular how similar, some of the challenges that you're having to deal with in getting your assessment and your approvals for OT, how similar that is here for a lot of us who are more used to working on weapon systems and weapon support systems. The those same kind of challenges you talked about with the fact that you still have to have controls in place despite the fact that no one could actually access it to.
Right. And like I said, the binary thing, well, and some of it's really ridiculous. War story wise, I know at a plant that I worked at, the first plant that I was a contractor at, there's recorders, and what recorders do is they take analog inputs. In other words, no digital coming in, no TCP/IP, just varying voltage levels, and they run a pin down a sheet of paper, literally a pin down a sheet of paper that rolls through it. You'll see them, those round things on the wall. When you see the movies where they're shot in a power plant, those are recorders. The more modern ones actually scroll a sheet of paper and either wind it up or fan fold it down on the bottom. And it's a hard copy record of what happens because the regulators don't really trust electronic stuff. The computer things, that's technology that wasn't invented in the 50s, so they don't really trust it. So they want literally pen on paper or printhead on paper. Well, these things don't network with anything, nor do they cause anything to happen. They just record it. And that record is what we call a quality document, but it's not even required during as for emergency preparedness, but they're part of one of those critical systems. And there are literally hundreds of them in older nuclear power plants before they had the big data loggers. At one plant I know, there are 4 people whose entire full-time job is to go around and document and update the passwords every 30 days. And these passwords are 4-digit numerical passwords, 1 through 9, 4 digits. They have to change them every 30 days. 4 full-time equivalent people working in a nuclear power plant. Even the janitor has to be able to pass a urinalysis test, and that's usually worth about $23 an hour. And it's probably going to be worth more now that McDonald's makes that much. So you're looking at that plant is spending in the neighborhood of $400,000 or $500,000 a year to apply a control to something that is no risk to anything, and it doesn't make a lick of sense. But they're binary. It's a digital thing in a critical system, therefore control must be applied, unless it's incapable of being applied. Now, I personally, when I do those plants, I call those 4-digit things, I don't call them passwords. I call them anti-intrusion devices or blocking aids. Because as soon as I call it a password, I have to apply the control. But since it can't meet the complexity requirements for a password, I don't call it a password and I don't credit it with being one. So I treat it like a device that doesn't have password. And since it's in the control room, it's in a 24-hour day manned, video monitored, and arm guarded place. Ta-da, I'm covered. But I didn't do their assessments. Yes, it's ridiculous.
Okay. I think that's all the questions that we've got here for this evening. I want to thank you for taking the time to speak with us.
Oh, thank you. Like I said, I ran through as fast as I could, skipped stuff, and I got to admit, I missed my notes, but I couldn't figure out how to access them on the fly. So good thing I did a dry run earlier today, or I'd have been totally out of luck. Well, it was a pleasure. I'm glad you guys invited me. One of these days, I'm going to come down there and visit your rocket museum because that thing looks cool.
Alrighty. Thank you.
All right. Well, I guess that's it for the day. So
I
thank you,
will
and you guys all have a great evening.
open it up again for since I cut off the questions earlier for Chuck's point. If y'all want to go ahead and ask your questions now, Jacob, I think you had the question, didn't you?
I do have a question, and I will give Tim thanks and a shout out, and just note that with some of the work that goes on with the TVA down here, I know that there are probably some opportunities for some crosstalk and cross pollination when it comes to nuclear related things. I've crossed paths with a number of people who do nuclear related work with TVA down here. So I thought this was a good talk, and there's certainly other people besides just those who many of us come in contact with that are doing missile defense or FBI work and DoD stuff. But I know there's a lot of stuff in the TVA realm that is very, very relevant to this. My question is, I guess, more for the board. I'm curious if we have any other events that are uh, scheduled in person. I saw that Karen Williams is on. I was wondering if maybe at some point there would be an opportunity for a joint meeting, maybe with Cyber Brews or something like that. I think that a
We're
handful of us
actually
would
looking
probably.
at doing that next month. We're working
There you
on
go.
with her right now to see if we can't get that put together. We're also trying to work with some of the other organizations here in town to have uh, joint meetups. I forget what it's not ISACA, but it's the,
ISSA.
yes, ISSA. We've had a couple of meetings where we've like tried to get out notices to have a joint meetup with those organizations. Unfortunately, ISC squared requires that if we're going to send out a notice that we have 2 months of notice time to get an announcement out to them in order to get it out to the rest of the membership. And generally speaking, those organizations only scheduled their events a couple of weeks out at most. So we've run into a couple of problems just running into the resources that ISC squared gives us. Because for any of y'all who don't know, ISC squared does not release any contact information for any members in the area to the chapters. We're entirely responsible for getting your contact information if you want us to contact you, and getting that creating our own mailing lists and all of that stuff. Anyway, they take member privacy very seriously, and that's one of the reasons why you don't hear a lot from us, is because there's so many hurdles just getting information out to you guys.
Yeah, Jacob, let me hit on that as well. And that's why I was really trying to plug the idea that we need to have contact information for the active members of the chapter. Okay. Um, that's why out on our website, there will be a form where you'll be able to fill that kind of stuff in. We have bits and pieces of it now. We can grow more of it, of course, but it's so we have a way to reach back out to you guys and to the email address that you want us to go to. What also hit us when COVID hit was there were people who have during that time changed their employment and their employers. Okay. And many people were giving us addresses of their employer's email. Okay. So in my case, if I was with boozallen.com, it's gone because I'm no longer with Booz Allen. Okay. So we're trying to move to a preference to have your personal email address. We're not going to give it out either, but we will use it to try to stay in touch with you and let you know when the meetings are going to be.
All
Any
right,
other
cool.
thing? Did you want
Nothing
anything
else
else?
from me. Thanks.
Cool.
Alrighty. Thank everybody for joining here this evening. One really quick thing I wanted to throw out at everybody before we go is just to give you an idea of the kind of thing that this technology has the ability to revolutionize. You heard him talk about how expensive a 12 unit of these new small modular reactor power system could cost. Just fun fact for you, the Belfonte nuclear generation station that we have out over there in Hollywood, Alabama, I didn't know this, not an operating nuclear power plant. You see smokes and light and everything coming out of that all the time. It is not producing power. TVA spent something like, it's well over $6 billion in original. That's not adjusted for inflation. Originally spent $6 billion constructing that plant and partially constructing those reactors before giving up on completing them because of the kind of nuclear regulations that we've got in place here, and it just not being financially feasible to complete those kind of plants. So we might actually be building nuclear power here in the U.S. again fairly soon. Be interesting to see. Thank y'all for joining us. Y'all have a good evening.
All right, thanks, you too.